before we get into the math and the formulas and all that, I want to ask you what you think might happen in this situation. So suppose a 5,000 kilogram truck is going to collide head-on with a 1,000 kilogram sedan. Which one do you think will experience the greater impulse? For the sake of safety, we will assume that there are no people and only crash test dummies inside of these vehicles. So let's see if we can answer that question by first figuring out, well, what is this idea? What is this new concept of impulse? Video, as it said on the first slide, is only going to look at translational impulse. So there is a rotational version, but we will get to that when I do a whole video on the angular versions of momentum and impulse. So change in momentum, and the symbol for that is capital J. I don't know why. It is a vector quantity, though, as you see with the arrow above it. And here's a crucial distinction that you have to make sure you're clear about. Impulse is the total change in momentum. It's the total change, not the rate of change. So a good analogy that might help you understand the difference there is, if I talk about how much my position changes, we call that displacement, but the rate at which my position changes is my velocity. Clearly, displacement and velocity are not the same thing. Also, we've already introduced a formula that tells us what the rate at which momentum changes is equal to. And this came from Newton's second law, which we rearranged in the last video. And we found already that the rate of change of momentum is net force. So, to summarize it all, the rate at which momentum changes is net force. The total change is impulse. Formulas that we can use to calculate impulse. Because it's a change in momentum, you'd probably start with the obvious delta P, and that is valid. It's not super useful, but it's valid. We can also replace the P with mv. We know momentum is the product of mass and velocity, so it's delta, the quantity mv. We can also use this formula that we introduced in the last video, and that I mentioned on the last slide, that the net force is the rate at which momentum changes with respect to time. Algebraically manipulate that a little bit. I'm going to move my dt to the left side, integrate both sides, so these d's become deltas here. And what we get is that the total delta p, the total change in momentum, which again can be written delta mv, because p is the same thing as mv, is the integral f of t dt. And so we end up with these four completely different expressions, all of which are equivalent. These first two aren't really useful. These two, that's a j and delta p, these are really just definitional things. So, you know, that's good to know, but you don't really need these. These last two expressions, though, this is where you're going to solve 95% of all momentum and impulse problems. Integral of f dt is equal to delta mv. So a lot of questions are going to ask you to calculate the impulse of something, and there's two huge, very frequently used strategies that you can employ to figure out impulse. The first is if you're given a function of force with respect to time. How could you go from that to the impulse imparted on an object over some known or specified time interval? Well, since the expression for impulse is integral f of t dt, if you want to know the impulse, you just integrate the function you're given over the interval of time that it specifies. And we'll do an example of that in a moment. What if you're given a graph? Well, integration is really nothing more than the process of finding the area under a curve. That's all it is. So you just count the squares under the curve. Let's try to apply the first of those two strategies. We're going to start with the function for the amount of force with respect to time acting on this object, and it's given by 3t plus 5, and we'll assume force is in newtons and t is in seconds. The object has a mass of 4 kilograms. I'd like you to pause the video here and try to solve parts A and B, and I will pick it back up with the solution in a few seconds. Part A says to calculate the impulse delivered during the interval 0 to 2 seconds. So like we said on the last slide, what we want to do is integrate, and we have limits 0 to 2 seconds of the expression 3t plus 5 dt. This is just power rule, so I'm not going to walk through how to do that. I think we can all integrate this function. We have 1.5 t squared plus 5t from 0 to 2 seconds, and that means you're really just evaluating it at 2, because when you plug in 0, this all goes to 0. So you end up with the impulse from 0 to 2 is 16 Newton seconds, which again is the same units as momentum, right? We don't usually say Newton seconds for momentum. We say kilogram meters per second, but they're the same thing if you expand a Newton to what it is, kilogram meters per second squared. Okay, part B. We're going to find the velocity now that we know the impulse. We also know that this thing started from rest. Here it is, started from rest at time 0. So the total change in its momentum is 16 Newton seconds, and if it began at rest, it means it started with no momentum. Therefore, at 2 seconds, it has a total of 16 Newton seconds of momentum. That's how much it's changed during this interval. So we'll use the formula delta mass times velocity, where we know the mass to be 4 kilograms from the prompt. And V here is the thing that has a change, right? That's what the delta will apply to in this case. So I'm going to change this to V final minus V initial, or subscript specific to the prompt, velocity at 2 seconds minus the velocity at 0 seconds. So that's the change over the interval 0 to 2 seconds in the velocity. We're going to do 0 for the initial velocity, and the final velocity is what we're solving for, plugging in 4 for the mass and 16 for the impulse. Solving for V2, we get 4 meters per second. Now we're going to try the other strategy. We're not going to start with a function. We're going to start with a graph this time. I'd like you to pause the video again and try to solve this question. And when you're ready, resume. We're going to go through the solution now. So we know a few things about the block. We know it starts at rest, and it goes to a final speed of 16 meters per second, and it takes 5 seconds to do that. We also know that there's this varying force, non-constant force, that acts over the interval 0 to 5 seconds, and that's represented by this red line on the graph down here. Well, we can't use the integration strategy from the last question. So what do we do if we have a graph? We can use what an integral means. We can use our understanding of what this expression on the left actually means. It means from 0 to 5 seconds, what is the area under the curve for the force versus time graph. That's literally what an integral is. So we're going to just take this area, and I just split them into two shapes because I don't know the formula for the area of a trapezoid, but if you do, go nuts. So I just do triangles and squares and rectangles, and that's what I've done here. So what was the area of this first part, this blue triangle? Well, it would be 1/2 base times height. So 1/2 times 2 seconds is my base, and 80 newtons is my height, and that gives me a total of 80 Newton seconds of impulse from 0 to 2 seconds. That means at the end of 2 seconds, remember we started from rest, at the end of 2 seconds, my total momentum is therefore 80 Newton seconds. Okay, then the force goes to be 80, and it stays a constant for the next 3 seconds. But I'm still exerting a force and therefore accelerating the object. So it's going to continue increasing in speed because of this unbalanced force of 80 newtons for 3 more seconds. How much does its speed change? That depends on how long the net force is applied, in this case 3 more seconds. So we all know the formula for the area of a rectangle. and if you multiply these, you get 240 newton seconds. And again, that's only the impulse, or how much the momentum changes from 2 until 5 seconds. That's only for that 3-second interval. Since we want to answer the question from 0 to 5 seconds, we just sum these two impulses, and we get a total of 320 newton seconds. So that went in here for the integral f of t dt. That is the integral. That is the area under the curve. On the right side, delta mv, well, that again means the mass, which is a constant, times the change in v. You can do questions, by the way, where m is the thing changing, but we haven't seen those yet. Anyway, so m is going to be the constant. I'm going to move that up front. And then in the parentheses here is the change in velocity, where again I've used the subscripts to denote what times we're talking about. So the velocity at 5 seconds, final, minus the velocity at 0 seconds, initial, is the change in velocity. And we also know the velocity at 5 seconds to be 16 meters per second. That's in the prompt. Plugging that in, I get a final answer of 20 kilograms. Automobiles use the idea of impulse to make cars safer. I want to show you an example of that. So first, I'd like you to pause the video, read and answer the question on the screen. So this question is kind of like asking what weighs more, a pound of bricks or a pound of feathers, right? You know, it's almost a trick question because you know, just because it makes sense, that it's worse to hit a brick wall than to hit a pile of pillows. Why there's a pile of pillows on the road will lead to another video. But there is, and this car is going to accelerate, but much, much more slowly, right? Car B accelerates more slowly. But which one is going to have more impulse? Well, one of the equations for impulse is the change in mass times velocity. Let's just check those values. Mass, same for both cars. Velocity, well, this would be the change in velocity, so let's make sure we're using the change. Both cars start at 30 meters per second. Both cars decelerate to rest. Therefore, they have the same mass and the same change in velocity. They have the same impulse. So why is it more dangerous to hit the brick wall? Why is that worse? Well, because there's another formula for impulse too, right? It's the integral of force dt. And that means that even though they have the same change in momentum, they didn't change their momentum in the same amount of time. Look over here at the end of the prompt. One car comes to rest in 1/4 of a second. The other one comes to rest much more slowly. This is 60 times slower than the first car. So if you think about force and time, if you increase the amount of time that it takes to change your momentum, you must also decrease the force. And since force is the cause of acceleration, increasing time during a collision decreases the acceleration. That's why it is more dangerous to hit a wall, is because you stop suddenly. The way that manufacturers of cars use this idea to make cars safer is with this thing called a crumple zone. So here's a model I found online. Crumple zone basically means that in the event of a collision, either head-on or if you're rear-ended, the hood or the trunk cover, I guess the hood of the trunk, whatever you call that on a car, this thing, the back hood. Anyway, it's going to literally crumple like an accordion would. You know, instead of just sort of pushing straight backwards into the cab of the car, you can imagine how dangerous that would be. It's going to crumple up, kind of like this. Why would that make it safer than a hood that did not crumple? Well, in terms of impulse, this should make a lot of sense, right? If you can increase the time it takes to stop, you decrease the force. And again, that means you decrease the acceleration. The more time it takes you to come to rest, the crumple zone here, it will see sort of what's supposed to happen in the event of a crash. And some actual examples of cars that have been in accidents and the crumple zone working. So you see this one during a collision. I like this one the best for that reason. Look here on the left side. That hood is clearly crumpling up, right? It kind of goes up and down. This one is another good example. It sort of goes up, down. And this one is just a model of what should happen, but it's the same idea. You're basically turning the hood of your car into a spring, and that will slow you to rest more gradually. That's why it's safer.